I'm very jealous of Professor Lee, who have talked about so much good words. And here, here is the background. We actually first proposed a special session for this interspeech, but it got rejected. And but during we prepared for this one, I actually looked up a lot of different papers of the speaker modeling for different speech applications. So I want to just put them together and try to have a discussion with all of you. And here is today's outline. The first one, I will just give a very simple introduction about the background of speaker modeling and its applications, and then I will go through some observation and analysis across different applications. But this part mainly comes from the papers from the other groups, for example, the Shinji's group and also Mark's group. And then I will just post all the limitations from the previous papers of the current speaker-related task, and finally give some discussion on the possible future directions of the guideline principles when we want to design a maybe not speaker embedding, but speaker representation or some other kind of form of stuff for the target applications. Okay. For the speech modeling, well, it's just aimed to capture information related to the identity of a speaker while neglecting the other attributes. But however, when we are now using different speaker embeddings for different tasks, we actually want to preserve certain kind of attributes instead of removing it now. So here I just put a figure. Here previously, we just do the speaker modeling, no matter whether it's a traditional vector or deep speaker embeddings, or we can also do the joint speaker modeling with the speaker-related tasks. Usually, we will relate speaker recognition and speaker derivation, test speaker VAD, this kind of stuff to the speaker modeling. But okay, I want to stress that the generation tasks, such as the text-to-speech and voice conversion, where we need to know the identity of the target speaker, is also quite related to this speaker modeling. And I just gave a very quick review of this one. For the speaker verification, we just want to compare two different embeddings here. And for target speaker extraction, the embedding works as a condition to notify the system which speaker to extract. And for the speaker generation, we also need to give the system the speaker information in a certain format, and it's similar to the voice conversion. And for the speaker derivation, Professor Lee has introduced a lot. It can be the embeddings, it can also be some frame level embeddings pre-extracted for the target speaker VAD systems. So, for the speaker recognition task, we usually say it's a successful story, but because all these systems are designed for this task, so we have experienced different architectures from TDNs, Ikaba TDNs, and all the different variants of the ResNets. And we are now training on larger and larger scale data sets, such as VOSLab, and then move to Professor Lee's WASP-Blink, which already extends to 100,000 speakers. It's a quite large data set that I can imagine during my PhD study. And we have different kind of loss functions to make the speaker embeddings more and more discriminative. And during this training, we also find that it's more robust to different environmental factors because we have introduced different augmentation methods and also some improvements in the loss function also. And I would say it's quite a well-structured embedding space that we can currently use simple cosine distance to do the scoring, and but there are still some limitations when we rethinking about this kind of embeddings. For example, it's over smoothing. We don't have the really some details of this speaker embedding. So usually what we have learned for these speaker embeddings, it cannot directly be applied to even to test the dependent speaker verification system because we are not normalizing all the details, including the content information, and definitely it's a loss of prosodic information, as just mentioned by Professor Hongyi Li. They have a separate speaker embedding, and they have a separate acoustic tokens to model all the other different attributes. And for the emotion, yeah, there will be no emotion here. Although there are a lot of emotion recognition people trying to use the architectures from our speaker recognition community, they have to retrain all the system on the emotion data. Yeah. So when we go to the other tasks, except the speaker recognitions, we're still this kind of we're performing speaker embeddings work. Well, here we usually have this one embedding fits all fallacy. We just assume that the speaker embeddings are optimized for the recognition are universally effective. That's why all the people doing different tasks, when they first do the speaker related task, for example, do the type speaker synthesis or type speaker extraction and release stuff, they first trying to just find a pre-trained speaker encoder to extract different speaker embeddings and compare this kind of embeddings to see which one was better. But actually none of them get a very concise explanation that which one might perform better, because the results are quite related to the performance on the speaker recognition task. So here comes the critical question: what makes an ideal speaker representation, not for the speaker recognition task, but for all the different other tasks? So here the core dilemma I listed here is that for the speaker recognition, we want to just maximize the discrimination and minimize the intra-speaker variance, and it should be robust to the other other attributes. But for the generative task, for example, for the speech synthesis and for the voice conversion, we actually want to capture not details. Actually, when I saw the paper, the VAL E, if you know, for the speech synthesis, they use a audio prompt instead of a speaker embedding to do the generation. And in that demo page, I just found that if the prompt contains noise and the resynthesized voice also contains noise. So previously, I actually believe this should not happen, but they claim that is a feature instead of a bug. So I don't know whether we need to preserve those kind of noise information. And also here we for that kind of synthesis, we also want to keep the rich and expressive representation. We want to maintain the expressiveness of the prosody from the original speaker. But for the target speaker processing stuff, the relation to the speaker recognition stuff is that the speaker recognition, we actually want this absolute discrimination. But for the target speaker processing in a mixture, it's really like only 2 or 3 speakers. Maybe we don't really need this kind of absolute discrimination. We just want relative one to discriminate the target speaker with the other background speakers. So here, what we want to do is to maximize the correlation with the target speech in the mixture, and it can be even more compact representation, because here usually for speaker recognition we have embedding sizes of 500 dimensions, but for target speaker processing maybe we don't need those high dimension one. So now here the conflict comes: do we want to still optimize the speaker embeddings towards a discriminative objective function, or we want to also preserve some generative richness? And here I just listed some for different tasks. So maybe we want different kind of processing. And next one, I will just go through several observations and analysis across different applications from other papers. And for the text-to-speech one, actually the challenge is to generate a natural expressive speech that sounds like the target speaker. So the key requirements for such kind of application is that we need the timbre accuracy, but at the same time we want the system to have this prosodic naturalness and preserve this emotional expressiveness. And but there are some gaps here because the speech recognition embeddings, they just one embedding for the whole utterance and the dynamic features are just removed. And the emotional cues and style variation are also just removed. Here are some evidence because now especially for zero-shot TTS, not that many people still use speaker embeddings for this kind of system, but instead they all use different kind of acoustic prompts. These prompts can be encoded into different audio tokens depending on what kind of codec or what kind of tokenizer they use, but still they preserve the sequence information instead of only using the single speaker embedding. Here I listed some main findings from this paper from Moya, and they basically tried to use a lot of different speaker embeddings from the pre-trained models, and what they conclude is that the embedding choice actually doesn't affect the learning process because when in their experiments they actually just condition on the different embeddings, but the neural network are still optimized against the TTS objective. So they just found that no matter you use whatever kind of speaker embeddings, the results for the TTS are just similar. And they also find that there is a speaker leakage problem when whatever kind of speaker embeddings you are using. And they also tried this their short speech synthesis, and they just found all the speaker embeddings just doesn't work that well. So for voice conversion, yeah, it's similar, but voice conversion can be even more complicated because we always want to do this disentanglement, not only the speaker identity and the content, but we also want to do the disentanglement of the prostate, the accent, the emotion, and etc. Current approaches, there are different trials. The adversarial training, or you just add a gradient reversal layer to, let's say, resynthesis speech not sensitive to a certain attribute, or they just use multi-encoder architectures. These encoders can come from different pre-trained SSL models or speaker encoders. And but still, there are challenges behind the perfect disentanglement are actually impossible, and always they just find that there is residual speaker information when you finish the conversion. You can still hear something about from the source speaker, and the content speaker entanglement is still there if you want to do an automatic disentanglement instead of using an ASR model or using a speaker model separately. So, but here the question is that can we really achieve the perfect disentanglement? But I don't think so. But people are still working on this problem. And for the target speaker extraction, is actually, I would say this is the rise of the embedding free methods, and as Professor Li Ming has introduced, not in this talk, but they did a lot of good work on this target speech extraction, the embedding free methods. Basically, you just currently don't rely on the embedding anymore. You will rely on the sequence information. So this information can be encoded from the same encoder as a mixture encoder, and we also tried several different methods. For example, these multi-level representations. We also condition on the spectrogram directly, or the sequence of embeddings before the polling layer, all of these different sequence informations outperform the original utterance level embedding based methods by a large margin, at least like 2 dB. Also, there are some trials to use these SSL-based features, but the same thing is that when they use these SSL-based features, it's a sequence, it's not an embedding. So here, the key insight listed here is that the direct acoustic matching maybe it just can outperform the abstract embeddings. And here I also listed some main findings from this paper, and this paper is from Mark, from NTT, and what they have found is that the first thing is that if you really want to use this speaker embeddings, the SSL models with OM pre-training or this kind of dyno pre-training outperform supervised speaker models across all the target speech processing tasks. And they also have analysis on different tasks, the target speaker extraction, the target speaker ASR, and the personal VAD. They just found that the speaker reputation performance is actually uncorrelated to the target speaker processing task. Also, what they did is they also have some analysis on the speaker code effectiveness, which means they only consider the speaker closed setting. Here it works very well, even though it's only one single embedding, because you can just maybe, I would not say it's overfitting, but still one hot speaker code works very well. And if you look into their paper and look at the visualization of the speaker codes, it's basically not a cluster. It's even only one point for different speaker codes to do that way if you want to do the clustering. And here they also tried a way to do the optimization to automatically update the embeddings you import to the system. It's gradient-based optimization, and the performance can be significantly improved. Here I only list a number of WER, but for the other tasks, the TSE task and the other tasks, it also improves. So for the speaker derivation, here I only list some findings from these two papers. Also, they try to directly apply the pre-trained embeddings to the speaker derivation. The first finding is that they just find if you reduce the dimension, for example, when the original dimension is 256 and you reduce it to 20 dimensions with a very simple linear layer, something like that, it already helps improve the performance quite well. And here also the same observation is that the conventional equal average on MLC-SLM actually not unrelated to the DER, is actually negatively correlating with the DER, and they actually proposed an intro-session verification protocol to show that if you select the model based on this new protocol, it can rely the selection with the derivation need. What they did actually is just they assume that currently for the derivation stuff, you want to separate or you want to differentiate the speakers of the same recording within the same environment. So when you need to also construct a similar test set for MLC-SLM, they just chunk the utterance to several segments and use the segments from the one utterance as the positive pairs instead of the original pairs from different utterances, and use that one to compute equal error rate, and it helps. Also, they found the similar thing is that the contextual information helps, or here they just say it's frame level features helps. You just remove the global polling layers and use the conformal-based enhancer now you also don't get a single embedding. They have a sequence of 40. They produce 40 embeddings for every three second segments, and the DR can be reduced to by 10% on 4 different data sets. So after this kind of observation across different applications, what we can summarize is that the first limitation is that the current trend or the current research on the different speaker-related applications is over reliance on this speaker recognition optimized embeddings. Of course, it's easy to use. For example, I have a toolkit called with speaker, and also for Xing, you have a toolkit called ESP-net speaker. All we claim is that one good thing for the toolkit is you can easily have this off the shelf usage. You don't need to care about how we get this embeddings, how we train the extractor, just extract and use it for all the other tasks. Yeah, it's very easy to use, but you can only get suboptimal results for your own task, and so the cost is just limited innovation and the task mismatch here, and also lists several evidence, the USEF1 and the prompt-based TTS. And the second limitation is actually the inadequate dynamic feature capturing. As mentioned by several pages of slides before, actually all of them mentioned that the fine grain or the sequence level representations outperform this kind of embeddings because the averaging problem or this aggregation of the whole sequence to a single embedding can collapse the diverse acoustic informations, and a lot of information are lost, as I mentioned earlier in several pages. And for the possible impact on applications is that your TTS model maybe is not so expressive. Actually, about this comment, I discussed with several friends from the industry. If they still use this embedding-based methods for their online system, the only reason is that it's more stable. But the output, the expressiveness is really, it just cannot be compatible with those use acoustic prompts. But if you use acoustic prompts, there will be many bad cases that they don't know how to deal with. It just come out of nowhere. So here, also for the voice conversion, it's quite limited for this expressiveness. That's why we want to have different types of encoders, whisper encoders and Hubert encoders, and we don't want to use the output of the last layer. We want to use the output of the first several layers because we believe that it contains more expressiveness, and the prostate it's not natural, and it's actually more flattening. And here the critical question is that how can we preserve this kind of intro-speaker variability while maintaining the discriminative ability? And the third limitation is that this kind of disentanglement challenges. The fundamental complexity is that speech factors are inherently intervene. They are not independently encoded. During this conference, there are several papers. They try to make the speaker embeddings explainable by designing the different dimensions of the speaker embedding to contain different meanings of attributes, but it's quite preliminary results, and they just cannot compare with the results with what we previously did, because what the data set they can find is very small, because you need all these attributes labeling for that training data set. So they just evaluate on the data set they design by them own. And so after these three limitations, I want to have some discussion on the possible future directions. The first one is actually the task specific representations. Previously, yeah, as I mentioned, that everyone is just using the speech embeddings optimized for the speaker recognition task. But here, maybe we just want to design a specific kind of speaker representation, not embeddings to different tasks. For TTS, maybe we can use hierarchical representations and multi-level encoding, and also try to make this representation procedure aware. And for voice conversion, maybe we will do this kind of disentanglement focused. And for the target speech processing, I just mentioned, I think the context-aware modeling is really important, because currently there are also different words. They don't rely on the speaker identity, but on the semantic tasks or even on the keywords. So also here, I also list one thing called adaptive representations. Here, the thing is that usually when we do the target speech processing, no matter it's target speaker extraction or target speaker ASR, the speech of the target speaker in the mixture, usually the environment of the process or something like this are quite different with your enrollment. So how do we do this adaptive representation when you are processing using this system and try to close the gap between the enrollment speech and the speech in the mixture can be very important for this one. We did some preliminary results by just automatically updating the target queue when you do the online speaker extraction. It works well, and but still there are some problems to solve, and there are also actually I think at least 5 papers they just try to use raw acoustic feature spectrograms to do the extraction. It works very well. I don't know whether this is the final solution for this task. So for the direction 2 is that should we do this disentangled and interpretable features, and to move from the vector to interpretable and controllable representations, as I just mentioned. But here, if we want to derive this kind of features, we need to answer these questions: what constitutes a pure speaker identity, and how do we measure the disentanglement quality, and what are the other fundamental limits to when you apply this kind of embeddings or representation to your own application. So, and the final direction is that enhance the robustness, because we want to, no matter this speech synthesis and voice conversion as the root, but for the cocktail party problems, it's really challenging to work on real world conditions. Here we need to train the speaker modeling with larger and more diverse data sets. That's why the data sets such as post-blink are really needed for today's research. And we also want to do this effective and scalable data management and simulation. I saw Professor Lee's slide using the Post-blink 2 to do the data simulation for the speaker derivation. I think that would be one direction, because we don't want to only rely on data sets such as Library2Mix or WSG, something like this. We need to try real world data sets and then to solve the real world problem. There is another one. Go. And so another one is that whether we can to first train a unified model and then do the adaptation to different tasks. Yeah, this is just a very big picture, so I don't know how to do it. And so one solution might be just build a common foundation model and then do the task-specific adapters. Then the problem will become that for the foundation model, what do you want to capture in this model? Whether it's pure speaker identity, and then for the target task, you add different attributes to the foundation, or it contains a lot of different attributes, and you remove a certain attributes to get your your final task-specific speaker representations. And I will just quickly go through several principles here. Is that it's just related to what I have taught in the directions. The foundation is that we need to clearly define for your task what kind of representation you want and what aspects of speaker identity are most important for your application. And the second thing is to balance the discriminative power with the generative flexibility, and it's still depend on what kind of task you are working on. I don't think, for example, for the target speaker extraction or processing or speaker recognition, you really need this kind of generative flexibility, but for some generative tasks, you need it. And the final thing is holistic evaluation. I think some researchers already noticed this stuff, because usually we just measure the speaker similarity with the equal error rate or mean DCF, but for the target speech, for the TTS or the voice conversion, we still measure the same thing, but whether this kind of speaker similarity measured by the cosine distance really relates to what humans feel, it's actually not that case. So also in this year, I just saw one paper. They want to predict the perceptual speaker similarity based on the Vocella data set. I think that's a good start. And also we need to do more challenging benchmark data sets, and we want to include these human-in-the-loop evaluations. Yeah, and it should be the multidimensional assessment. So the key takeaway here is that the answer is that when embedding doesn't fit all, and there are limitations, and I've discussed about several possible directions and approaches. So I think that's all for my talk, and here I just listed several open questions which I don't really have answers. Yeah, thanks.
Okay, thanks for the basic talk. We will learn a lot from it.